Okay, so today's notes are multiplying and dividing radical expressions. It's section 6-2. And our content objective is to multiply and divide radical expressions. And our language objective is to explain that process with correct terminology. So let's start by defining one of our properties of multiplication for radicals. So if we have the nth root of A and the nth root of B, and they are real numbers, then we can multiply the nth root of A times the nth root of B, and we will get the nth root of A times B all under the same radical. So what this is saying, if we're taking the same, or if the two radicals have the same index, we can multiply their radicands. So if they have the same index, we can multiply what's under the radical or the radicand. So I'm going to do a couple of quick examples of this. So I'm not going to write out all the steps for how we do this, but I'm going to show you how this works with a couple quick examples. So I'm asking, can you simplify the product of the radical expressions? So to do this, first one I'm going to give us, number 1, if we had the cube root of 6, sorry, that's a 6, not a b, the cube root of 6 times the square root of 2, can you multiply those? And the answer is no. The indexes are different. So again, this does not work if the indexes are not the same, so do not multiply them if your index is not the same. The second example has the cube root of -4 times the cube root of 2. And so yes, we can simplify this, and I will show you how. So since I have two things being multiplied, they have the same index, I can do -4 times 2, all under the same radical. And when I multiply -4 times 2, I get the cube root of -8. And as you may know, the cube root of -8 is -2. So I can fully simplify that to -2, and that would be our fully simplified form of the product of those radicals. Okay, so it's not always going to be this straightforward. I'm going to do a little more complicated example here. So again, I want us to simplify this. But this time we have the square root of 72 x cubed y squared times the square root of 10xy cubed. So again, I can multiply these because they have the same index. It's nothing in there, so it implies it's a square root or that there's a 2 in the index. So the first step I'm going to do is, like we just did, check that the indexes are the same. And since they are, I'm going to multiply the radicands. So when I multiply that, I get the square root of 72 x cubed y squared times 10xy cubed. So at this point, I'm going to simplify this with the laws of exponents. So I want to combine all my like terms more or less. I mean, they're not exactly like terms, but I want to see how many total x's I have, how many total y's I have, and the actual coefficient when I multiply that all out. So simplify with laws of exponents or properties of exponents. So when I do that, I get the square root. 72 times 10 gives me 720. X cubed times x, I'm going to add their exponents since I'm multiplying two things with the same base, so I get x to the 4th. Y squared times y cubed, again, I'm going to add their exponents since I'm multiplying two things with the same base, so I get y to the 5th. So that's my simplified, or when I simplify what's under the radical, but now I need to simplify what's under the radical to get things out. So I'm going to rewrite as terms, since it's the square root, I'm going to try to rewrite as many terms squared as possible. So So when I do that, I know 720 is divisible by 144, and I know 144 is a perfect square. So I'm going to rewrite 720 as 144 times 5, because then I know I can take the square root of that term. X to the 4th, I can rewrite that as x squared squared, as you may remember that we've practiced. 5 isn't divisible by 2, so I'm going to take out one of the y's, and then I'll have y to the 4th, which I could rewrite as y squared squared. So if you saw what I did there, since this was not an even number, I couldn't divide it by 2, I took one out, and then I rewrote what was left as y squared squared. So I rewrote it with terms squared. And now for my last step, I'm going to simplify the root, or simplify the radical, by taking the square root of each term. So the square root of 144 I know is 12. The square root of x squared squared is x squared, so that squared cancels. The square root of y squared squared, again, is y squared. But then notice that I still have those two terms that don't come out from the radical, so those stay under that root. And this would be my fully simplified form. Since I took everything that could come out of that square root out, this is my fully simplified form. So as you can see, it gets a little bit trickier when we get to larger numbers, but this is what we practiced the past 2 days, so hopefully it's not too terrible. All right, so I'm going to flip the page for the next one. While I'm writing this, if you can send me a quick email and let me know that you're listening, that would be helpful. So I know that you're actually listening to these notes. So this property says if you take the nth root of a and the nth root of b, and again, they are real numbers, and in this case, b cannot be 0, then we can say that the nth root of a, sorry, that's supposed to be the nth root of a, so index, not a coefficient, over the nth root of b is equal to the nth root of a over b. So just like with multiplication, if they had the same root, I could multiply them. Here, if I have the same root, I can also divide them. So the same property applies, it's just now we're dividing instead of multiplying. So I'm again going to do a couple of quick examples. So for the first one, again, I want us to simplify. So the first one, I have the square root of 18 x to the 5th over the square root of 2x cubed. And when I rewrite that, I can write it all under to the same two things, 18x to the 5th over 2x cubed, but now it's the square root of that whole thing. So here now I can actually just divide out and simplify this using my laws of exponents. So I know this 18 divided by 2 is 9. I know x to the 5th divided by x to the 3rd. I'm going to subtract their exponents since they have the same base and they're being divided. I subtract their exponents. So I get x squared, and then that square root is still there. So I have the square root of 9x squared. I know the square root of 9 is 3. The square root of x squared is x. So my fully simplified form would be 3x. Another quick example, just to make sure we're all on the same page, if I have the cube root of 162 y to the 5th over the cube root of 3y cubed, then again, I can rewrite that as the cube root of the whole thing, 162 y to the 5th over 3y cubed. I'm again going to simplify it. 162 divided by 3 is going to give me 54. Y to the 5th minus y cubed, or divided by y cubed, I subtract their exponents, and I get y cubed again, squared. Sorry about that. Y squared. And then I'm going to rewrite this. 54 doesn't have a perfect cube, so instead I'm going to rewrite this as the cube root of 27, which does have a perfect cube, times 2 times y squared, sorry. So then I'm going to take the cube root of 27, which I know to be 3. So I have 3 cube root of 2y squared. And I can't take out any of the y's since it's squared, not cubed. So that would be my fully simplified form of that expression. All right, so the last thing I want to talk about in these notes, or last new thing for these notes, is rationalizing the denominator. And this can be kind of tricky. There are some cases where it's not too bad, and there's other cases where it can be a little confusing. But the whole rationalizing the denominator is a process that's pretty, I guess, common, or it's kind of expected for the notation that you leave a rational denominator, meaning you don't have a square root of something that you don't leave any roots in the denominator. So this just means when you're rationalizing it, we're getting radicals out of the denominator. So notationally, it's not good in math to leave a square root or a root in the denominator, so rationalizing it allows us to get that out. So my example that I'm going to use to show you how to do this, I want us to write the cube root of 5x squared over 12y squared z in simplest form. And to do that, I want to rationalize the denominator. So as you can see to start, there's nothing I can divide out, or there's no way to easily get these things out of the denominator. So I'm going to have to rationalize it. The first thing I'm going to do is separate it into two roots. So I'm going to rewrite this as the cube root of 5x squared over the cube root of 12y squared z. And now I want to make everything in the denominator into a perfect cube so that when I take the cube root, I can take everything out. So my goal is to multiply everything in the denominator by what it needs to make it a perfect cube. So that's step 2, multiply. And when I'm multiplying in the denominator, I can't only multiply in the denominator. That's not allowed. That'd be completely changing the value. So I'm going to multiply the numerator and denominator by that, because then that's like a form of multiplying by 1. So I'm going to multiply the numerator and denominator by the terms needed to make the denominator a perfect, to make terms in the denominator a perfect cube, or to make perfect cubes in the denominator. So in this case, I'm going to multiply by the cube root of, to make, there's another simpler way I could try to find the lowest perfect cube that I could multiply to get, or I could multiply 12 by to get a perfect cube. But for simplicity's sake, I'm going to multiply that by 12 squared, y and z squared, because I know then my exponents on each term will be a cube. And I have to multiply the numerator by the same thing, so 12 squared y z squared, because then I'm just multiplying by 1. I'm not actually changing the value of my fraction. So when I multiply that out, I end up with the cube root of 144 times 5, which is 720, y, or x squared, sorry, y z squared, over, then I have the cube root of 12 cubed y cubed z cubed, which then becomes the cube root of 720 x squared y z squared over 12yz. So now I can take the cube root of each term. I've rationalized my denominator. The only problem is, because I didn't find the lowest possible number I could multiply by 12 to get a perfect cube, I'm going to have to do some simplifying with my coefficients. So my denominator is rationalized, but it's not in its simplest form. Sorry, I skipped writing a step. I need to simplify under the radical. So now I need to simplify the coefficients. So I need to check if there's a perfect cube that goes into 720, and there is. 8 is a perfect cube, and that goes into 720. So I'm going to rewrite this as the cube root of 2 cubed times 90, because 8 times 90 gives me 720, and then the rest of my terms stay the same. So again, I'm just trying to take out any perfect cubes that go into my coefficient, and then I'll take out that 2. So then I have 290 x squared y z squared over 12yz. 12 and 2 are both divisible by 2, so I will divide that out, and I get 90 x squared y z squared all over, if I divide 12 by 2, I get 6 yz. And that would be my fully simplified form of that radical. And that's all we have to do for that. That's a particularly tricky example, but we'll have some more practice with different ones like this in class. Make sure you write down any questions, comments, concerns you have so we can go over them together.